we prepared the MicroTorch deep learning framework that we built from scratch. If you open this video and you know nothing about the MicroTorch, I recommend you to check this playlist from the beginning. And now it's time to build our first training loop. Stack a few linear layers and crack the spiral pattern. Loss functions, also known as cost functions or objective functions, are used to measure how well the model's predictions match the true labels. During training, the goal is to minimize this value using optimization techniques, thereby improving the model's performance. To make a clear definition of the loss functions, let's first of all reconsider the expected risk definition. An expected risk measures the average loss of your model on the true data distribution. Right now it's right over here. This P data, it's a true data distribution. We consider in the expected risk not just the distribution inside the training set. Yeah, we just suggest that we have some hypothetical probability distribution that describes our data. Let's focus on this part, and this is saying that take the expected value, or let's call it average, over all possible input-output pairs x and y that are drawn from the true data distribution P data. And the whole formula, it means that on average over the entire true data distribution, how much error does my model make? Yeah, we just trying to measure how much errors we have compared to the true hypothetical data distribution. Most of the time we don't know the full data distribution. We approximate this using the empirical risk, the average loss over a finite training set, because we have most of the time, yeah, we have no any real data distribution, yeah, and we can approximate it based on the train set, and that it calls the empirical risk. It's all the time we use the empirical risk on practice. Inside this formula, all the pieces are defined in our code. For example, this f of x of I, it means that our model that predicts a value based on the data point xi, and yi is the true, is the label from our data set. Loss function, it's our loss function that we run and compute the difference between the predicted value and the true label. And then this one, we just sum up all of the pieces together and compute 1 over n. We just compute the average in this way, yeah? And you can see how we express the same formula in the code, yeah? It's just a bunch of strange symbols, yeah, but it's pretty simple to express in the code. Let's say that this L, this symbol that denotes the loss function, we express it as the cross-entropy in our code. This Y predicted, it's bunch of labels from the model's prediction, or this F of X of Y. And Y of Y, it's true, it's predicted values, and we compute the cross-entropy loss and compute the average, the mean of the result, yeah, it's right over here, 1 over n, it's our mean, yeah. So you can compare both of these pieces, yeah, this one it's the mathematical definition, this one is bunch of code that implements this schema, this formula. If you're summing the individual loss, you are computing the total loss across the batch. This is not normalized, so it's like not equivalent to empirical risk, because we're missing this 1 over n factor, and it's exactly the same schema, yeah, but without this factor. and we can express it like this. We compute the same cross entropy between the y predicted and y true labels, and then sum the losses up. On practice, we use three different options. Mean, that just standard training setup, it's most common choice. Mean normalizes the loss across batches, providing consistent scaling regardless of the batch size. Sum, we use sum if you are manually accumulating gradients, for example, over multiple small batches before an optimizer step. Summing the losses ensures the gradient accumulate property across all batches. And the last one, it's none, that allows you to work with each sample's loss independently. For example, if you need let's say, if you want to apply the custom reduction strategy, or you need this individual losses for debugging or masking, you can use the none, and it returns you back that each sample's loss individually. Okay, now let's define reduction loss, and we receive loss as the tensor class, and we have the reduction parameter as the literal, and we use mean, sum, and let's say none. So, and by default, let's install it as the mean. Okay, and we return back the tensor. Yeah. And now let's use if the reduction equals mean, we need to return loss dot mean. If reduction is sum, we return loss dot sum. And last, we just return loss without any reduction. It means that we apply this none strategy. Now I want to build the base loss class. Let's define class loss as the module children. We need to define init constructor, self as the first argument, then reduction, and we need to use the same literal data type for the reduction, and we know that we need to install self.reduction as the reduction. Maybe we can create a common data type, reduction as the literal data type, and then we just install reduction here and here. Okay, then let's create the compute loss method. We receive self as the first argument, predicted as the tensor, and the target as the tensor 2, and we return back the tensor data type. But now let's erase not implemented error. Yeah, so just because this method must be implemented in the children class. Then let's define forward method. We have self, the same type signature, predicted, target, and we return the tensor back. So if predicted shape not equals to target shape, we must raise the value error, because input and target must have the same shape. Yeah, and just debug information about the current shape of the predicted and target. Then let's compute the loss. We need to call self dot compute loss, and we put predicted and the target. Okay, and we return the reduction loss, and we put loss as the first argument, and as the second argument we need to put self dot reduction. So we compute loss based on the compute loss method inside the loss and apply the reduction loss. It means that this forward method, it's just basically unified method for all of the loss, yeah? The only method that we need to define is compute loss in the children loss class. Binary cross-entropy loss is used for binary classification tasks, where each output is a probability value between 0 and 1. The main feature of cross-entropy in common is right over here in this log function. I have a video about cross-entropy. You can check it if you wanted to know more details about the behavior of the cross-entropy and this log function. So here I just want to implement the class binary cross-entropy loss, and it's just the children of the loss class. Let's now define the constructor, and we just need to install the reduction parameter. Let's use the mean. Yeah? And the only parameter that I want to put inside the binary cross-entropy, it's an epsilon parameter. Let's define it as float and install by default 1e to the -9 power. And probably for the reduction, let's install the mean, yeah, and put this argument to the parent constructor. Yeah, we can just put this reduction. Okay, then let's install to the self this epsilon value. And as far as I remember, the only method that we need to implement, it's right over here, this compute loss. Everything else we implemented in the forward, and it's common for all of the losses that implements the parent loss class. Okay, and we need to build this formula. First, I want to use this epsilon to clip for the predicted values. We need to clip values between self.epsilon and 1 minus self.epsilon to prevent corner cases where our prediction equals 0 or 1. We need to compute loss, and let's follow the same notation. Negative y, its target, times the predicted dot log. So we call the predicted dot log, it's exactly a log of our y hat of our prediction. Then plus 1 minus the target, because y it's the target value, times the 1 minus predicted dot log. And we implemented the same formula, yes, step by step. We use y as the target, predicted log as this log of y hat, plus 1 minus target, 1 minus 1, times 1 minus predicted log, yeah, because this y hat, it's the log. And we need to return the loss. And I think that this is the implementation of the binary cross-entropy.